Welcome students. Today we are going to study Ultraviolet and Visible Spectroscopy Part 3. We'll be discussing today first the transition probability, then chromophore and then oxochrome. So let us discuss them one by one. First we are discussing transition probability. Depending upon the symmetry and the value of Emax, the transitions can be classified as allowed transitions and forbidden transitions. Now, what are allowed transitions? Molecules don't absorb just any radiation. They absorb only such radiations which have appropriate energy to excite the electrons to allowed higher levels. These are the transitions which have values of extinction coefficient Emax more than 10 to the power 4 and are called allowed transitions. They generally arise due to pi to pi star pi antibonding transitions. Pi to pi antibonding transitions are of high intensity, that is Emax 10 to the power 4, because both the orbitals pi and pi star, that is pi antibonding, lie in the same plane. Therefore, such transitions are geometrically favorable and are allowed transitions. For example, in 1,3-butadiene, the absorption at 217 millimicron and the Emax 21,000 is an example of allowed transition. Now next comes the forbidden transition. These are the transitions having Emax value less than 10 to the power 4. N to pi star transitions generally belong to this category. N to pi star transitions occur with low intensity, that is Emax less than 10 to the power 4. Since N and pi star orbitals, that is non-bonding and pi antibonding orbitals, are perpendicular to each other, the jump of one electron from non-bonding molecular orbital to pi antibonding molecular orbital is geometrically poor. Therefore, N to pi star transitions are said to be forbidden transitions. A saturated aldehyde or ketone shows an absorption band at 290 nm at Emax less than 100. It involves a N to pi star forbidden transition. N to pi star transition near 300 millimicron in case of carbonyl compounds with Emax value between 10 to 100 is the result of forbidden transition. Now next, let us study a chromophore. All those compounds which absorb light of wavelength between 400 to 800 millimicron appear colored to the human eye. Exact color depends upon the wavelength of light absorbed by the compound. Originally, a chromophore was considered any system which is responsible for imparting color to the compound. Nitro compounds are generally yellow in color. So clearly nitro group is the chromophore which imparts yellow color. Similarly, aryl conjugated azo group is a chromophore for providing color to the azo dyes. But now the term chromophore is used in a much broader way. Now chromophore, it is defined as any isolated covalently bonded group that shows a characteristic absorption in the ultraviolet or the visible region. The absorption occurs irrespective of the fact whether color is produced or not. Some of the important chromophores are ethylenic, acetylenic, carbonyls, acids, esters, nitrile group, etc. There are two types of chromophores. First type, chromophores, in which the group contains pi electrons and they undergo pi to pi star transitions. Such chromophores are ethylenes, acetylenes, etc. Now next type of chromophore which contain both pi electron and n non-bonding electrons. Such chromophore, they undergo two types of transitions, that is pi to pi star and n to pi star. Examples of this type are carbonyls, nitriles, azo compounds, nitro compounds, etc. In compounds of the type saturated hydrocarbons like alkanes, the absorption occurs around 150 millimicron as a result of sigma to sigma star transitions. For compounds containing such atoms as oxygen, sulfur, nitrogen, absorption occurs around 190 millimicron as a result of n to sigma star transition. There are no set rules for the identification of a chromophore. The change in position as well as the intensity of absorption depends upon a large number of factors. These are, first we can say, spectrum consisting of a band near 300 millimicron may contain 2 or 3 conjugated units. Second factor, absorption bands near 270 to 350 millimicron with very low intensity Emax 10 to 100 are due to n to pi star transitions of the carbonyl group. You can see this in this table, the chromophore C double bond O. The transitions are shown, the absorption max and Emax values are shown. Next factor, simple conjugated chromophores such as dienes or alpha beta unsaturated ketones have high Emax values, that is from 10,000 to 20,000. Next factor, the absorption with Emax value between 1000 to 10,000 shows an aromatic system. When aromatic nucleus is substituted with groups which can extend the chromophore, the absorption occurs at still higher values of extinction coefficients. Some of the chromophores with their respective absorption maxima and extinction coefficients are given in this table. So just have a look. In detail, the chromophores are written, the transitions are written, absorption max, Emax values are written in this table. Now next comes the oxochrome. An oxochrome can be defined as any group which does not itself act as a chromophore but whose presence brings about a shift of the absorption band towards the red end of the spectrum, that is longer wavelength. Or we can say that a saturated group with non-bonding electrons when attached to a chromophore changes both the wavelength and the intensity of the absorption band is called an oxochrome. We'll study it with the help of examples. For example, OH, NH2, OR, NHR, NR2, etc. The absorption band usually becomes intense, that is, Emax increases and shifts to longer wavelengths, that is towards visible region, due to the presence of oxochrome. Now, for example, nitrobenzene absorbs at 268 nm, while para-nitroaniline absorbs at 381 nm. So here, amino NH2 group is an oxochrome. One more example we can see. Benzene shows an absorption maximum at 255 millimicron and Emax 203, whereas aniline absorbs at 280 millimicron, Emax 1430. So here also, amino NH2 group is an oxochrome. One more example you can see. In aniline, the lambda max is 280 nm and Emax 1430. And in anilinium ion, the lambda max is 254 nm and Emax is 160. So here there is a difference. In aniline, NH2 acts as a chromophore, but in anilinium ion, since there is no lone pair on nitrogen atom, so the values are less in anilinium ion. We may compare oxochromes with promoters of catalysts. Promoters themselves have no catalytic ability, but they improve upon the activity of the catalyst. All oxochromic groups contain non-bonding electrons. Due to this, there is extension of conjugation of the chromophore by sharing the non-bonding electrons. So here this is an example, CH2 double bond CH and CH3 twice. So here there is a lone pair on nitrogen atom, and you can see by the help of arrows it is shown that there is sharing of the non-bonding electrons, and ultimately the CH2, that is on CH2 group the electron pair is there and a negative charge is there. So these were some of the examples. Some more examples you can do. One more example is Transazo Benzene. The lambda max is 320 nm and Emax is 21,000. But in case of trans-para-ethoxyazobenzene, the lambda max value is 385 nm and Emax is 42,000. So there is an increase in the value of lambda max as well as Emax. Why? Because the presence of OC2H5 group and oxochrome increases the value of lambda max as well as Emax. So I hope by the help of all these examples, the concept of chromophore and oxochrome is clear to you. Thank you so much.